International Atomic Time is a high-precision atomic coordinate time standard based on the notional passage of proper time on Earth's geoid. It is the basis for Coordinated Universal Time, which is used for civil timekeeping all over the Earth's surface, and for terrestrial time, which is used for astronomical calculations. As of 30 June 2015, update, when the last leap second was added, TI is exactly 36 seconds ahead of UTC. The 36 seconds results from the initial difference of 10 seconds at the start of 1972, plus 26 leap seconds in UTC since 1972. Time coordinates on the TI scales are conventionally specified using traditional means of specifying days, carried over from non-uniform time standards based on the rotation of the Earth. Specifically, both Julian dates and the Gregorian calendar are used. TI in this form was synchronized with universal time at the beginning of 1958, and the two have drifted apart ever since, due to the changing motion of the Earth. Operation. TI as a time scale is a weighted average of the time kept by over 400 atomic clocks in over 50 national laboratories worldwide. The clocks are compared using GPS signals and two-way satellite time and frequency transfer. Due to the averaging, it is far more stable than any clock would be alone. The majority of the clocks are cesium clocks. The definition of the SI second is written in terms of cesium. The participating institutions each broadcast, in real time, a frequency signal with timecodes, which is their estimate of TI. Timecodes are usually published in the form of UTC, which differs from TI by a well-known integer number of seconds. These time scales are denoted in the form UTC in the UTC form, where NPL in this case identifies the National Physical Laboratory, UK. The TI form may be denoted TI. The latter is not to be confused with TAR, which denotes an independent atomic time scale, not synchronized to TI or to anything else. The clocks at different institutions are regularly compared against each other. The International Bureau of Weights and Measures combines these measurements to retrospectively calculate the weighted average that forms the most stable timescale possible. This combined timescale is published monthly in Circular T, and is the canonical TI. This timescale is expressed in the form of tables of differences UTC for each participating institution K. For the various unsynchronized atomic timescales, errors in publication may be corrected by issuing a revision of the faulty Circular T or by errata in a subsequent Circular T. Aside from this, once published in Circular T, the TI scale is not revised. In hindsight, it is possible to discover errors in TI, and to make better estimates of the true proper time scale. Doing so does not create another version of TI, it is instead considered to be creating a better realization of terrestrial time. History. Early atomic time scales consisted of quartz clocks with frequencies calibrated by a single atomic clock. The atomic clocks were not operated continuously. Atomic timekeeping services started experimentally in 1955, using the first cesium atomic clock at the National Physical Laboratory, UK. The Greenwich Atomic Scale began in 1955 at the Royal Greenwich Observatory. The International Time Bureau began a time scale, trademark or AMP, in July 1955, using both local cesium clocks and comparisons to distant clocks using the phase of ELF radio signals. The United States Naval Observatory began the A1 scale 13 September 1956, using an atomicron commercial atomic clock, followed by the NBSA scale at the National Bureau of Standards, Boulder, Colorado. Both the BIH scale and A1 were defined by an epoch at the beginning of 1958. It was set to read Julian date 2,436,204.5 at the corresponding UT2 instant. The procedures used by the BIH evolved, and the name for the time scale changed. A3 in 1963 and Ta in 1969. This synchronization was inevitably imperfect, depending as it did on the astronomical realization of UT2. At the time, UT2 as published by various observatories differed by several hundredths of a second. The SI second was defined in terms of the cesium atom in 1967, and in 1971 the name International Atomic Time was assigned to a time scale based on SI seconds with no leap seconds. During this time, irregularities in the atomic time were detected and corrected. In 1967 it was suggested that nearby masses caused clocks to operate at different rates, but this was disproven in 1968. In the 1970s, it became clear that the clocks participating in TI were ticking at different rates due to gravitational time dilation, and the combined TI scale therefore corresponded to an average of the altitudes of the various clocks. Starting from Julian date 2,443,144.5, corrections were applied to the output of all participating clocks, so that TI would correspond to proper time at mean sea level. Because the clocks had been on average well above sea level, this meant that TI slowed down by about 1 part in a trillion. The former uncorrected time scale continues to be published under the name EAL. The instant that the gravitational correction started to be applied serves as the epoch for barocentric coordinate time, geocentric coordinate time, and terrestrial time, which represent three fundamental time scales in the solar system. All three of these time scales were defined to read JD 2,443,144.5003725 exactly at that instant. TI was henceforth a realization of TT, with the equation TT equals TI plus 32.184 s. The continued existence of TI was questioned in a 2007 letter from the BIPM to the ITUR, which stated, in the case of a redefinition of UTC without leap seconds, the CCTF would consider discussing the possibility of suppressing TI, as it would remain parallel to the continuous UTC. In 1961, UTC began. UTC is a discontinuous timescale composed from segments that are linear transformations of atomic time, the discontinuities being arranged so that UTC approximated UT2 until the end of 1971, and UT1 thereafter. This was a compromise arrangement for a broadcast time scale. A linear transformation of the BIH's atomic time meant that the time scale was stable and internationally synchronized, while approximating UT1 means that tasks such as navigation, which require a source of universal time, continue to be well served by public time broadcasts.